Welcome everyone. Today we're looking at bouncing balls. It's just one extra little section of vertical motion where now we're going to have a ball, it's a bouncing ball, that's going to bounce. So it's continually changing directions and I can hear the groans already. It's okay. This is a nice section. So, have you thought about how the motion of a ball changes when it bounces? There's lots of things at play here because there's forces, there's a change in acceleration, there's a bounce or there's a collision. Can you hear collision means momentum? Lots to consider. Okay, let's get there. So, we've done everything else now and we're looking at bouncing balls. When we consider a bouncing ball, these are our keywords. Position, where is it? Displacement, velocity, acceleration due to gravity, that doesn't disappear, impulse, and momentum. And right now you're going, but we're doing vertical projectile motion. Physics is all interconnected, okay? We sometimes ignore some parts to make it a bit easier for us. But actually, in reality, everything's connected. And that's what we need to look at. So, here we go. When we look at a bouncing ball, we're going to have to consider what happens with acceleration due to gravity, what the graphs look like, and then there's collisions, okay? Graphs being, of course, velocity time graph, position or displacement time graph, and acceleration due to gravity. It's always acceleration due to gravity that gets us with this section, okay? So, acceleration due to gravity for a bouncing ball, okay? And most of the time, we're going to ignore the time it spends on the floor, just because it makes it a bit easier. What that means for us is that acceleration due to gravity is a constant 9,8 meters per second squared down. More so than any other section, you tend to think it changes direction. Most of you are okay with it being thrown up, it comes back down, we're good with it. It's when an object gets thrown, hits the floor or surface, and then bounces back up that we sort of go, what happened to gravity? Hasn't disappeared. It's still part of the motion. Then, of course, our position versus time graph. Here, our graphs become a little more complicated because we now have multiple times when the ball's going to go up and get slower and come back down and get faster. So it all depends on what we do with the ball, what our direction, positive direction is, but essentially what our graphs end up looking like, okay, is we have our position, we have time, and I always take original direction of motion as positive because I just like to stick to the same thing every single time. These graphs tend to look like the motion of a bouncing ball. So if I say to you, I throw a ball up, and then it comes back down, and it bounces, okay, on the floor. I'm going to take the floor as my reference. I'm going to take up as positive. So what happens is I throw it up from a position. It goes up, it slows down, it comes down, it hits the floor, it bounces, and it comes down, and it bounces, and it comes down, and then it bounces. And we could carry on forever because we all know balls don't just bounce once or twice. And if you look at that, it looks like a bouncing ball. It's going up and down and up and down. Same thing as before. We've just usually only maybe looked at one part of the graph or one motion. Now we're just adding the extra things in. It's not more difficult, there's just a longer graph, so we're looking at more motion, but it's still a curve. It still has a decreasing slope when it gets slower and an increasing slope when it gets faster. That's the same. Velocity time graphs become interesting for us because now, and let's using the same one I just told you. Now we have an object that has an initial velocity that's up, and it's now going to get smaller. So I'm saying that it gets to 0, it hits the ground, and now this is the key. There's an immediate change in direction. Then it goes down, immediate change in direction, and it comes down. And the thing with this is that they are straight lines. They are all parallel because acceleration due to gravity is 0. We don't draw complete lines here because we're sort of ignoring the time it spends on the ground, making our life easier, okay? And then your acceleration graph, and this is the one you always struggle with. Now that should just be time, give me a second. So, I made a positive, so that means my acceleration is negative the whole way through. I'm ignoring the time it spends on the ground for now, okay, because that just makes our life easier. But acceleration due to gravity is not going to change, no matter what the motion of the object is, okay? Then, of course, we can include momentum and impulse in this section, and kinetic energy. We're going to get to that later, but it is part of it, okay? And I want to show you how it all works together. And on that note, we're going to take a short break, and then we'll do some more in-depth look at this. I'll see you in a couple of minutes. Welcome back. I hope you're ready to do an investigation into a bouncing ball, and hopefully this will make it sort of make sense to you, okay? So what we're going to do is we're going to investigate the physics of a bouncing ball, and I'm going to include things like momentum, I'm going to include impulse, I'm going to include kinetic energy, because it's important for you to see a whole picture, okay, and not just isolated bits of physics, because everything works together. So here we go. I have a 150-gram ball, so it's not very big, dropped from a height of 1.55 meters. Now, I know you can't see from where you are sitting from the screen, but that's how tall I am, so I know it's dropped from about this height, okay, just as a reference. It hits the floor and is in contact with the floor. That should say floor, not fall. Anyway, for 0.2 seconds and rebounds, so it hits the floor, then bounces back up at 5 meters per second. Now it's dropped, so my very first velocity is 0. The ball then hits the floor a second time and now rebounds at 4 meters per second after being in contact for 0.2 seconds again, okay? Now this may not be complete. I've tried to make these values as accurate as possible, but there may be some little errors. It's all right. So what we need to do is I need to know the velocity when it hits the floor for the first time. So I want to draw some graphs. So I know my initial velocity was 0. I want to know what its final velocity is. I'm going to take down as positive because it was dropped, which means my acceleration now is 9.8 meters per second squared. I don't know delta t, but I do know delta y because we said it was 1.55 meters. Okay, I want the velocity when it hits the ground for the first time. Going back to our equations of motion, the best equation is delta y, vi delta t. No, I can't use that one. I'm lying to you because I don't actually know time. So that's not a good one. The one I'm trying to get to is Vf squared equals Vi squared plus 2a delta y, where Vi is 0. This is 2 times 9, 8 times 1, 5. 5. Absolutely need my calculator. So we've got, let's just get rid of that. The 0 we don't need to worry about. So we have 2 times 9.8 times 1.55. That gives me 30.38, but I'm going to need to square it. So now I'm going to take the square root of that answer. And, oops, we get 5.51. That's what I'm going to use. So my final velocity is 5.51 meters per second down. What I also need to know is the time taken. At this point, I have several equations I can use. I'm just going to use the one that, quite frankly, is the easiest, which is Vf equals Vi plus a delta t. Of course, you could use delta y equals Vi delta t plus a half a delta t squared, the other one. But then there's a square on the t, and let's just make maths easier. So 5.51, that's 0, 9.8. To get time on its own, I'm going to divide 5.51 by 9.8, and I get 0.46. So, seconds. So what I've worked out now is I know initial velocity, I know the velocity it hits the ground with, and I know how long it took to get there. So that's important pieces of information that we need to keep. Now, I want the maximum height after the first bounce. They told you, if we go right back to the original one, it rebounds at 5. So, the initial velocity now is minus 5. Why am I saying minus? Because I took down as positive, okay? I can't change it because I'm trying to find something else. So now this is minus 5, okay? Gets to its maximum height, which is Vf, which will be 0. I know my acceleration is 9.8. I don't know the time it takes to get to that height, but I want delta y. So, looking at the information, again, I'm going to go Vf squared equals Vi squared plus 2a delta y. Vf is 0. Vi is minus 5 plus 2 times 9, whoopsie, I keep doing that, 9.8 delta y. I know minus 5 squared is 25, so I'm going to take it over. It's going to be minus 25 equal to 19.6 delta y. We definitely need our calculators. So we've got minus 25 divided by 19.6, and we get minus 1.28. I'm going to round off to 2 decimal places. I'm happy with that being a minus because I said down is positive, it's now moved up. So the maximum height is 1.28 meters, okay? We want the velocity when it hits the floor for the second time, so that's the next thing, oh, that's the third time, so let's just go here. Velocity when it hits the floor for the second time. Well, this one's not a calculation, okay? It left the floor at 5. It's going to hit the floor at 5. So that velocity is going to be 5. Straightforward. Now we want the time taken to hit the floor for the second time. So we're just going to do it over here quickly, where we go VF equals VI plus A delta T. My VF is 5. My VI was minus 5. A is 9,8. This becomes 10. And so delta T is going to be 10 divided by 9.8, and we get 1,02 seconds. So that's the time it takes to go from the floor, get to the top, get back down. So that's the second time it hits the ground, the first bounce. Then we get to, oh, it's over this side now. Okay, so now we get here, and now they want the maximum height after the second bounce. We go back to what I gave you. For the initial velocity of the second bounce was 4. Okay, we know VF is 0. We know A, and actually that's minus 4 because it's going up. A is 9,8. And we want delta T. Eventually, we want delta Y. So we've done this more than once. And we go VF squared, VI squared plus 2. Oops, don't forget the square. Delta Y, that's 0. And this is minus 4 squared plus 2 times 9,8 delta Y. 4 squared is 16. Okay, so minus 16 divided by, 19.6. And now it's only minus 0,82, so it's significantly lower. And I'm okay with that. All right. Velocity when it hits the floor for the third time. It left the floor at 4. It's going to hit the floor at 4. So VF is a positive 4 meters per second. Time taken to hit the floor for the third time. So VF equals VI plus A delta T. That's 4. That's minus 4. 9,8. Delta T, calculator, okay, that's going to be 8 divided by 9.8, delta, oopsie, it's going all over the place, it's getting very excited. So delta T, 0,81 seconds. Why did we do all of this? So that we could put that information together on a graph, okay? So, velocity time graph. And we're going to do this very quickly. Was dropped. Initial velocity was 0. Bounced, hit the floor at, we worked this out, give me a second, at 5,51. Bounced, left the floor at 5. Oops. Got to 5, bounced, got to 4, and then it hit the floor again. So this is 5. This value here is minus 5. Not minus 5, it's plus 5. That value is minus 4. This value is plus 4. And then, of course, it hit the ground again. So that's where it hits the ground. All getting very messy. But what I want you to see are these lines, okay? And we could put times in, but we're running out of time, and we will put in all the values we learned, okay? My velocity time graph now changes. So it started at 0. We realized what its maximum height was. It bounced, and it bounced again. So this height was the first height, which was 1,55 meters. Don't forget this is delta y, and this is time. This height was the second height we calculated, which was 1,28, and this one here was 0,81. Not even vaguely to scale, but that's okay. We'll live with it, okay? The acceleration time graph, here things are a little different because I know when it's in the air, it's at 9,8 meters per second. Every time it's in the air. But then there's moments where the acceleration changes. And I don't want to get too caught up with that because that's the time it spends on the floor, okay? So for all intents and purposes for us, it's a constant. We are going to ignore, in reality, we are going to ignore the time it ends on the floor. I put the time in because we want to look at what happens with momentum and impulse. Okay, so with that information I've got, I can absolutely work out how its momentum changed, what force it experienced, and what its impulse was, because I know the time in contact with the floor. Okay, so that makes life a little bit easier for us. And those are the things we would be able to work out, but we're not going to worry about them. So, lots of calculations, but we got to see what the graphs would look like. So now, we're going to take a short break to catch our breaths, and I'll see you in a couple of minutes. Welcome back, everyone. Now we're going to dive, no pun intended, into bouncing ball problems. So we're going to gather our thoughts, and off we go. So here we go. A ball is thrown upwards from the top of a building. The ball bounces on the floor, and the graph shows the velocity of the ball from the moment it is thrown upwards until it reaches maximum height again after bouncing the first time. What we need to realize, okay, balls bounce a lot. A ball doesn't just bounce once and then stops. We don't need to consider all the bounces to know whether you understand the science or not. So don't worry too much about the fact that it sort of just randomly stops. Just go with it, okay? So here we go. This is my graph. So what do they show us? I have velocity. This is my initial velocity. This is the velocity that hits the ground with. This is the velocity that leaves the ground with. This graph is telling me which direction I have to take as positive. They said to me that the object is thrown from a building, goes up, and then hits the ground below. That initial velocity is positive. That means up is positive, which means for this, my acceleration should be minus 9,8. But I've done something special with this one. You'll see in a second. So, first question, what is the initial velocity of the ball? Well, that's fairly straightforward. Initial velocity, we just had 5, so we would say, well, the initial velocity is 5 meters per second up. Don't forget the direction. use the graph. Use the graph means area or gradient, not equations of motion. So we want the acceleration from here to there. Acceleration is equal to the gradient of my graph, which means it's change in velocity over change in time. I don't put change in y over change in x because my axes aren't called y and x. I use what they're called. So, final velocity minus 15. Initial velocity 5. Final time 2, initial time 0. So I get minus 20 divided by 2. I can do this one in my head. And now I get minus 10. I'm hoping that someone's now going, but wait. Just now, a few seconds ago, you said that the acceleration needs to be minus 9,8. I've now got 10. Don't worry about it. Sometimes when graphs get drawn, okay, so this is the graph drawn from the motion of a ball. There may have been a mistake made in calculating the final velocity or in how long it took the ball to hit the ground. That's okay. But what we do need to take into account is that now, if I need to use this acceleration, I must use 10, okay? This is actually a past exam question. So this isn't just one I made up. They used this in an exam. What were they testing? Could you use information from the graph, even though we know we should have got 9,8? If I'd done this question and I'd gotten 7 or 12, I'd go, there's a problem. But 10, close enough, okay? We also used to use 10 just because it made the calculations easier, but now we want to be more accurate, which is why we use the 9,8. So don't stress too much about it. It should ring alarm bells, but then just go back, check. We haven't done anything wrong, so we're going to use it as it is. We good? Okay. Now they say use the graph to calculate the height of the building. Remember, my object went up and then came down. I want delta y. Delta y is the displacement. They're saying to me, use the graph. That means I need to use the area under the graph. And I'm looking at the whole motion when it hits the ground. So I need this little area, and I need that area. Okay, so this little block, and that little block. We good? So here we go. So I want delta y, which is going to be the area under my graph. So I have one triangle, and I'm drawing my, no, let's just draw that properly for you so that you can read it. Here we go, so it's a half base times height because we've got a triangle plus a half base times height. I'm just indicating the 1 and the 2 because I've got two different. The first one, now we've got to think carefully again because I need to know this time. That's the time it takes to get to the top of its motion. By 1 second, it's back to 5. So it's gone up, it left at 5. At 1 second, it's come back to 5. We know that the time it takes to get to the top of the motion is equal to the time it takes to get to the bottom of the motion. So it's halfway between 0 and 1, and halfway is 0,5. Okay? So here, I'm going to put 0,5. My height is 5. There we go. Now this is going to be 1,5. My height is minus 15. Okay, so we need our calculators, and we're going to go 1/2 times 0.5 times 5, and this is going to end up being minus 1/2 times 1.5 times 15, and I get minus 10, which is what I expected, but the question was, what is the height of the building? Therefore, my height is 10 meters. It's not particularly high. I calculate the time it'll take the ball to reach the maximum height after the first bounce. They want to know what that time is. Now they've said to me, calculate. I don't need to use the graph, okay? So I can go, well, time to get the maximum height, VF, equals VI plus A delta T. Remember, up was my positive, so maximum height is 0. That's 10. But now what? They said to us, well, we worked out that acceleration due to gravity was minus 10. I have to use that. Okay? That becomes minus 10 equal to minus 10 delta T. So delta T is 1 second, but they don't want to know, best value then would be 3 seconds. They just wanted to know, calculate the time it will take the ball to reach maximum height. It'll take 1 second to reach its new maximum height. Okay? Position time graph, well, we took up as positive. It went up, it came down, and it went up. We only go that far. Why? Because that's as far as the graph went, okay? This would be the 2 seconds. This is the 0.5. This height is 10. That's what we worked out. And this is time. And no, that's not 10. I'm lying to you. This is 10. We didn't work out how high it went. There we go. Pen. And this is position. So that's not so bad. I've probably drawn the second bounce a little too high, but we're not going to worry too much about that. And lastly, is the collision with the ball inelastic or elastic? Well, it's definitely inelastic. All right, why? Because EK isn't conserved. Velocity changes during the bounce. Okay, it doesn't leave the floor with the same velocity it hit the floor with. And on that note, sure, we've come to the end of this little piece. So now it's time for you to take a short break, and I'll see you in a couple of minutes. Welcome back. Let's do some more bouncing ball problems. I'm hoping it's starting to get there. Sometimes we've just got to think through it a little bit, and then it sort of makes sense. And remember, as with all science, practice, 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 and then practice some more. And it's fun. Well, I think it's fun. That's why I teach it. Anyway, so let's move on. Here we go. So I'm going to give you a velocity time graph which describes the motion of a ball that is falling from rest. In other words, initial velocity is 0. Falls from a height of 5 meters. It hits a cement floor and keeps bouncing. And then we've got some parts labeled on the graph. So let's look at the graph. Here's the graph. Now, if you look at this, This graph looks a little different to the ones we've drawn up till now. Why? Because over here, that isn't a straight line. It's been drawn at an angle. This graph is now taking into consideration the time the ball spins on the floor. We've ignored it when we drew the velocity time graphs before because generally it's really, really short. So we want to make life a little bit easier for you when we go and we analyze a graph, okay? But this is more accurate because it spends time, okay? What I do need you to see, okay, that's my velocity that it leaves the floor with. What this graph is telling me, okay, now listen carefully to me, down is negative. We dropped the ball. The ball moved down, and they're showing this velocity as being negative. This is very important. So before I even start any equations, we realize that up is positive, okay? I'm just going to get rid of this part. What we also recognize, this is where it hits the floor, this is where it bounces off the floor, hits the floor, bounces off the floor, okay? At this point, it's at the top of a bounce, and C is where it's spending time on the floor, okay? So this is one of those things where up until now we've told you ignore this, but this is the whole point of the fact that the ball hits the floor, it squishes, and then it unsquishes and bounces off. But it's got to squish and stop, then it can change direction. The things we tell you to ignore, but some of you are going, but that's not what happens when you ignore it. We're not ignoring it this time, okay? So, we've got it. Calculate the speed, direction doesn't matter, that the ball hits the floor with. Okay, so calculate. I can't get it off the graph actually. So we want final velocity. We know initial velocity is 0. We know acceleration. Now we've chosen down as negative. In fact, we didn't choose it. We didn't have a choice. Okay, they told us that. So this is minus 9,8 meters per second squared. And we don't know time, but what I do know is delta y. We've now got to think carefully about this. It's dropped from 5 meters above the ground. They said down is negative. That means this is minus 5. That's a biggie here. Looking at the information I'm given, I can't use an equation that has time in it because I don't know time. So again, we're going to use this one. Now I know some of you are going, how do I know what the equations are? They're on your information sheet. You're not expected to remember them. I know them because I've been doing this for a while, okay? But what you should be doing is working with an information sheet when you study and when you do problems, because then you get used to what it looks like. And really, the more you do this, these eventually will stick, I promise. So we want VF, VI is 0, minus 9,8, minus 5. So this is V squared. Now we're going to have to pay attention to some maths here. So I've got 2 times minus 9.8 times minus 5, and I get 98. Okay? I need to take the square root of this. You know from maths that when you take the square root of a number, you can either get a positive value or a negative value. We've got to look at this carefully because we know it is got to be a negative value. And they actually just wanted the speed. But I'm now going to take the 98 and I'm going to square root that answer, and I get 9,899. You know what, I'm going to keep 3 decimal places just to make it a little bit more accurate, because rounding this off will give me 9,9. I'm going to keep it as 9,899. All right, but they wanted speed. Speed doesn't matter about the direction, but speed must be positive. Speed is a scalar. I don't care about direction. Speed cannot be negative. Very, very important there. So now I know what the velocity is at B. Which point on the graph corresponds with the moment when the ball hits the floor for the first time? Here. That's when it's hit the floor. Between B and D, that's where it's spending time on the floor. So that's B. That's all they wanted, no explanation needed. At which point does the ball reach maximum height after bouncing? So here it's bounced, velocity 0, maximum height. That's E. That's straightforward. What happens during interval BD? Now, I've spoken about that a lot during this. During that interval of BD, that's when the ball is on the floor and experiencing an upward force that's going to change the motion of the ball. So it's the time it spends on the floor changing direction. So it's experiencing a force. Now, do you notice I'm not asking you to do anything with time here? Okay? I could if I wanted to, because I know that it hit the floor here at 9,899. Okay? I could very easily turn this into a momentum question, because I know what it hit the floor with, and I know what it leaves the floor with. I've changed in velocity. However, what didn't I tell you? The mass of the ball. Okay? There's lots of things we can do with these. It gets very exciting. Why is the magnitude of the velocity of D less than the magnitude of the velocity at A? Because kinetic energy isn't conserved. Okay? It's an inelastic collision. Very, very important. Kinetic energy isn't conserved. When you bounce a ball, you hear a sound. Kinetic energy is changing into sound. It's changing into heat because there's rubbing on the floor. Okay? What is represented by the gradient of the graph from A to B? Well, it's a velocity time graph. Gradient of a velocity time graph, acceleration. Specifically, acceleration due to gravity. Acceleration due to gravity. Oh, now they want the height. The height, we know initial velocity when it leaves the floor. We know final velocity when it gets to the top. We know acceleration is minus 9,8. We want delta y. We don't know time. So we would use vf squared equals vi squared plus 2a delta y. We know that's 0. So 7,6 squared plus 2 times minus 9,8 delta y. So I'm definitely going to need to put this on my calculator. So 7.6 squared, which I'm now going to put onto this side, so it's maybe I should just pay attention to what my calculator is telling me, because I didn't. Minus 57,76 minus 19,6 delta y. Let's divide by, 19.6. And we get 2,95. There we go, nice and simple. And that's it. Oof. Lots of work, lots of practice needed. Nice section though. So that's the end of this lesson for now, and I will see you again next time.